was born in Taiwan and immigrated to the U.S. in 1999. He left out the fact that he came as a high school student and then skated for 6 years with Disney on Ice and has done all kinds of other cool things. So if you want some ice skating lessons, this is the guy to talk to.
Yeah, free for all the power people, of course. Yeah.
With a dinner.
Yeah. Kenta is my student right now. Yeah.
He graduated from Missouri S&T at Rolla in 2011, in December 2011, with a BS, and from UIUC in December 2013 with a master's. He is currently working with Professor Zhu for his PhD, and his research interest lies in smart grid-enabled distributed reactive power support framework and conservation voltage reduction. So let's thank Max for
That's a very long, yeah. Thanks. Oh. Hi, good afternoon, everyone. My name is Max, and today I'm going to give you a presentation which I'm going to present in next week in Italy. It's a methodology of conservation voltage reduction performance analysis using field testing data. Before this talk, I want to give a special thanks to my wonderful advisor, beautiful advisor, Professor Hao Zhu. She really helped me a lot. And also the researcher, Richard Macomb, he worked in ITI. So the presentation outline, I will give you a little background and motivation about this research. And I will give you a little bit detailed analysis about what CVR factor is. And then we're going to go into our methodology of the sparse linear regression based on CVR analysis. This is basically called LASSO, and I will mention in the later slides. And then I will show you the numerical analysis, and then with the synthetic data and the field test data sets from Emeren to just show you the CVR factor. And then lastly, I will conclude my talk and with the conclusion and future works. So what is conservation voltage reduction known as CVR? So this is very easy, simple ideas. The CVR is a reduction of the power demand. If you do overtime, it's basically energy resulting from a reduction of feeder voltage. So if you can think about, this is actually IEEE 13 plot. I simulated this from OpenDSS. And on the bottom is the substation voltage. On the vertical axis is the real power demand in kilowatt. So basically, this model has a low model, zip model. It's a zip model. Basically, it's a constant impedance, constant current, and constant power. So any kind of type of load you can model with a zip. And then with a different coefficient, if you the voltage will have an effect on the constant impedance, and the constant current will have no effect on the constant power. So you can see that as I lower the voltage from the substation bus, substation node, as there's a voltage decrease, the power, real power consumed from the substation also decrease. So they have a direct relationship. Question? Oh, okay, okay, okay. So where was that? Okay.
Why is it a straight line?
Oh, because this is just simulation because it's zip model. The way I define each different node has a coefficient.
So it came out straight?
Yeah, it came out straight. Yes. It might be curved next time, but maybe I change the coefficient. You maybe.
A certain amount of each?
Pardon me, what do you mean certain amount of each?
ZI and P?
Yes, the ZIP is basically I use a residential.
One-third?
No, it's 0 point. I'm not sure the specific value. I use a paper that give me a residential zip model load. I just apply that to my IEEE 13 bus. It came out to be kind of straight, but not necessarily has to be. The next, so basically to implement CVR, right now you can do either a closed loop or open loop form. With a closed loop, basically use a smart meter from the last customer here. So you just want to make sure your voltage range is allowable, is NC standard between 114 and 126. So we can adjust the LTC, the low tap transformer from the substation, as long as you make sure that your last customer on the feeder don't violate the lowest limit, which is 114. However, in the United States, most of the feeder, most of the residential home receive too much voltage. When I say too much voltage, usually they're operating between 122 to 126. Now, there's a saying that, in the United States, if the higher voltage the higher voltage you have, it's much better quality, voltage quality. So they might not be necessarily true because if you do lower the voltage, sometimes if you do a CVR factor, you can see the energy reduction. But some people argue that if you reduce the voltage on the feeder, you increase the system loss because if the voltage drop, the current will increase, right? If you assume the power is the same. However, they did a study that if you have a mostly constant impedance load in the house, actually the energy saving is actually greater than the loss. I mean the cost. Okay. So comes to the benefit of CVR. Basically, save energy, so it improves the energy efficiency and also decrease the carbon emissions because you don't need sometimes you don't need your expensive generator if you have a peak load demand. Also, it's peak load shaving and also improve system reliability because by reducing the voltage, you actually extend the transformer's life because the core loss is actually going down. And also is avoid overload on the critical circuit because if you like this February in Chicago we have a chip area, right? So I work in the ComEd this summer. So basically what they did during the winter is actually they did the CVR on certain time because they cannot meet the demand. So in order not to shave the customer's load in the winter, so they actually did the CVR, try to bring the peak demand down. And lastly is actually lower customer's energy bill to make the customer happy. Now you might ask, everything here is actually kind of save the energy, save the customer's bill, energy bill. But what is good for the utility? Because the utility actually make money by provide energy to the customer, right? But if you don't use that much energy, then where does the utility make the money? So the money actually coming from the regulation because each utility right now has a certain regulation they need to pass. The government gives them a goal in like 1 year, in 5 years, in 10 years. If they don't meet the criteria of how much energy reduction in that period, they get fined, they get penalized. So they try to do many different things, many different schemes of the smart grid technology, try to save the energy and try to make their system more efficient. So this actually will help. So the CVR factor, so this is actually a metric to evaluate the effectiveness of the CVR in the certain feeder. So the definition is percent of change energy over percent of change in voltage. So if I say my CVR factor is 1, basically with 1% of voltage reduction, I get 1% of energy saving. And this should have a direct relationship. However, this is a very high variable depending on the feeder's load composition and system information. What I mean is that sometimes when I reduce the voltage, you cannot necessarily see a reduce of a power demand because there's a human behavior, there's a temperature. For example, now it's super hot day outside. If I reduce my voltage, if the temperature keep rising, I'm probably not going to see energy reduction because everyone going to turn the power on and you want to cool the building. So there's a lot of variation in the human behavior and also the time of the day and also the temperature outside. Also, it's a feeder topology. So it's challenging to obtain from solely numerical simulations. So what we propose in this research is, going back this, is just to show you a simple way to determine the CVR factor. This is actually coming from EPRI Green Circuit project. So they did actually CVR on and CVR off like every day. So day on, day off, day on, day off for like 2 months. So what they usually calculate is comparison method. They sum all the CVR on day, and then they subtract the CVR off day and do the averaging scheme. So this is a comparison method. So you basically just do on, off, and just sum all the energy up and try to find a difference. And this scheme is not very accurate because, like I said, you cannot assume today it's going to be the same as tomorrow. The human behavior, the feeder topology, the temperature, maybe the weekend, holiday. So they didn't take any consideration into this kind of a comparison model. So also, I want to show you just a typical CVR factor of different circuits. So this has been done by the Snohomish City and also EPRI and the NEA. So typical CVR factor is between 0.5 to maybe 1. The highest is 1.5 over there. But typical is, if you see 2 or like a negative, it should never be negative. If you see like 0.3 or 0.2, it's kind of low. But if you see 2, it's unreal almost. So what we're proposing out in this research is actually we define a power demand model. So this power demand model comes with different variables. So we have a temperature in the Fahrenheit in the test feeder at the substation substation, and we also have a voltage measurement at the test feeder bus. And this is very important. It's a PT ref. It's actually the reference feeder. So because if you do CVR, usually they have a reference feeder, they have a test feeder. So in the traditional way, you would do the comparison method, right? You would say you assume the test feeder has a similar behavior with your reference feeder. So then you do this over time, then you just basically find the different energy difference and subtract it, and then find the CVR. But in our case, I just use the power demand. Reference feeder power as an input variable. Then I have a season of the year with full season, so winter, spring, summer, and fall, and the hour of the day is 24 hours, and then a day of the week, Monday to Sunday, and lastly is a holiday. So this comes to this. So basically, this P stands for the power demand at the test feeder. And this X is basically the metric come with all the variable here. So we have 39 variable come with temperature, voltage, power, the test feeder, the reference feeder power, and the season, hour, day, and the holiday. And this model basically is a linear model. If you look at this, P is basically has a linear relationship. The beta 0 is the intersection, and this is O1 vector. So basically, it's a linear model. So what our job is actually to estimate the beta. The beta is the coefficient for the variables, right? So the most important one I'm interested in is the beta 2, because beta 2 is actually related to the voltage. Basically, that's the voltage sensitivity to load. That's what we try to estimate. If I can find beta 2, I can estimate the CVR factor. I will show you the equation later. Now, how to do this? There's many ways to do this, right? You can, if I just give you this to you, probably most of you just do the least square, because this is a straightforward. You can put it in MATLAB and it's done. However, that sometimes if you do least square, you have an overfitting error you don't consider. So I actually we use this method called the least absolute shrinkage and selection operator. So this is known as LASSO. So what it is actually we impose a penalty here, lambda, and this is actually with a norm 1 beta. So basically what it is if you change the lambda, varying the lambda from very small volume to very large, you can actually change the parameter of the coefficient. So this is a picture here. If I set the lambda equal to 0, basically that's just least square. So then you will get non-zero coefficient to the x, because that's what least square is, right? Try to minimize the norm distance. However, if I start to increase this lambda, basically you start to shrink. So this like blue diamond start to getting smaller and smaller and smaller. And you know the solution of this minimization is where this curve meet this diamond, right? So if this diamond become very small, eventually hit 0. So it's mean all the coefficient of the variable will go to 0. And so by varying this lambda, you actually define the path going from least square. And if you increase, eventually every coefficient will go to 0. So you can define the path. And usually, if you know that the strongest variable will go to the 0 last. In our case, since the reference feeder is very close related to the test feeder, so the coefficient of the reference feeder should go to the 0 last, which I will show you soon. So by doing this, the first thing we did is get the OpenDSS synthetic data. We purposely set the CVR factor in this case to be 0.715. So we know this for sure. This is a model case. So we have the data from OpenDSS. However, we don't have the reference feeder from OpenDSS, so we have to select the range. So we pick the low range from 2680 watt to 2700 watts. So this is a plot here. And we do our lasso regression. And our CVR factor come out to be 0.69, which is very close to the known CVR factor. We did this over different power demand range. So they all come out to be roughly 0.7. And it shows pretty much, because the 0.71 is the known value, and they are very close to 0.71. So it's pretty good. And this is the path I was talking about, the lasso path. So you start with, so this is when lambda is 0. So you do least square. So most of the coefficient is not 0. So by increase the lambda toward the left, you can see the path, all the coefficients starting going towards 0. So eventually the last one go to 0, which is the strongest one. So this one comes out to be this will be the reference feeder power. Which one? This one? This one? This is a reference, that's a coefficient for the reference feeder power. And then by use cross-validation, basically you can pick the optimum lambda. By just use tenfold cross-validation, you can pick one with the minimum error. And that's basically, that defines your model. Yes?
The DF scale, and then on the very top of the left plot, 1, 2, 7, 17.
Oh, this is the ranking of my input X. So because they are into like a temperature, voltage, and it basically tell you which one hit 0. Yeah, so basically it's just a number tell you which variable go to 0. And remember my number 1 is my reference. That's where it goes to 0. And also to show this model is pretty correct. I plot the autocorrelation plot for the error. The error is basically showing the difference between the actual power demand and the estimated one with my linear model. If you know a little bit statistic, the error should be random. You should have no correlation between now and the future. So this is direct delta function. Basically, if you see 0 here, it means it self-correlated itself with the highest value, and as the time goes on, it has pretty much basically less correlation with itself in the future. So this you can say the error is pretty random. It's a good model for the estimation. So this is a ranking for the input for the synthetic data. Because we are using just a range, so this really doesn't make any, this tells you the voltage has a strong correlation to the power. But because we only select a certain range, so really I cannot say anything about other thing. But then we actually use the real field testing data from Amarin feeder, input to this model, LASSO model. So this is a 13.8 kV feeder in central Illinois, and the loading going from 3.5 to 15.4 kilowatt loading, and it has a CVR of 0%, 2%, and 4%. Basically reduce, they either have no reduction, and sometimes they do 2%, sometimes they do 4%. There's no certain pattern. They just do this depending on their the condition of their load and the condition of the feeder. So we perform this on the same structure, and you can see the number 1 rank is the power PREF, same as our synthetic data. Then go to the season, and then you have hour 12, the temperature, you have hour 8, hour 20. The most important and the one interested in this voltage coming to number 13, and with a coefficient of 2.71. So with the CVR factor, once you can know this coefficient, you can lower the voltage by 1% and recalculate your power demand, find the difference, and you can calculate the CVR factor. And this, in this case, turned out to be 0.43. Yes? Oh, the rank. You mean this? So the rank actually determined by this graph. Who goes to 0 the last is the strongest variable. Does it make sense? Because basically tell you that's the strongest relation with your model, your output power. Because like if you see here, this basically tell you the day of the week and the hour of the day, and then the last one goes to 0. In this case, this one is PREF, which is your power from the reference feeder, because they are close track to each other. They are very close related, so they go to 0 less. Pardon me? Correlation coefficient. I would assume so. I would assume they have a very closely related, because you are assuming they should be a similar feeders. Yeah. And so, where was So in this case, the CVR factor is 0.43 for the Amarin case. So the conclusion for this talk is basically we develop a methodology to analyze the dependency of the power system load on several measurement and variables. The measurement goes into the day of the week, hour of the day, season, the temperature, and the voltage. And we obtain the voltage sensitivity information, and we use that voltage sensitivity information to find the CVR factor. In the future, we plan to extend this work to more flexible power demand model, accounting for the dependency of each individual variable For example, that in this case, I assume the temperature and season to be independent, which they are not. We know they are close related because the winter, your temperature should be lower. But for the beginning, for the initial research, we just assume everything is independent. But in the future, we might want to do a group lasso to make sure some certain variable is you group them in a different way. So I will answer any question you might have. Yes.
Where is the application of the coefficients we get?
Pardon me.
Whenever for actually, if they get the coefficient from the CVR,
Yes.
where can they apply the coefficient?
Usually the coefficient for CVR is for the utility. They got very interesting to see where you should apply for the CVR. For example, if you have a feeder, but most of the customer is industrial customer, which is the CVR is usually very low, and you basically don't bother with CVR. So the CVR factor give you where you should apply because depending on the feeder topology, depending on your load composition, you apply CVR to certain feeder, but not every feeders. But there's a research showing if you do apply CVR to the entire nation, that there should be a 3% energy reduction in the year. Yeah, that's from Pacific Northwest National Laboratory. Yeah. You increase the power demand. So they're actually in ComEd, they have run into a problem. They actually come up, there's a several case as negative CVR factor. I will come to it. But that doesn't really make any sense, right? Because if you reduce the voltage, you actually increase the power demand. But there's only one case. If you have the plasma TV, it's only one, you actually see the negative relationship. If you lower the voltage, you see the increase in power demand. That's plasma. Unless you have a plasma TV for every single load, yeah, you will have a negative CVR. But if you have a resistive load and what other like heater and resistive element, you should see a positive relationship. Yeah, okay, Professor Klein.
Actually, I got to challenge you on that. Everything we can see in this room, everything we can see in this room
Yes.
is running at its constant power load.
Yes.
And therefore, would show a negative CVR because if you try to lower the voltage, the power will stay the same, but the losses in the network will go up because the current goes up.
Okay.
And therefore, it'll try and draw more out of the network. And more industrial facilities, commercial facilities, and even residences are seeing more and more of that, right? Because everything in here has power electronics in it.
Okay.
That basically ignores any changes on the grid and just continues to operate that way. So that's not a fluke. ComEd is going to see more and more and more feeders that will show a negative CVR. So you're going to have to think about what do they do about that. I mean, the snapshot you have today is
Okay.
very fast, right?
Yes, I agree. But I think that the way they're arguing is they're not going to change too fast. So they want to, yeah.
I'm changing as fast as we can get them to change.
Thank you. Yes, Kai.
Kind of on that, did you calculate any crossover points? Because you have the zip model.
Uh-huh.
You calculate the crossover point where the constant power load as a portion of the zip model, those resistive losses overtake the savings you get from the I and the Z portion.
Yeah, but for this research is purely data driven. So we are not using, so the thing I showed you earlier, actually just for the purpose to show you that if I decrease the voltage, I decrease the power demand. But because the CVR is really hard, if you have a model, because you have to have an accurate model in order to find the CVR factor, because you don't know what temperature will be or the human behavior will be. So there's different kind of way you can evaluate the CVR factor. In our proposed, we are just purely data driven. We have no idea about the model, no idea about feeder. We just get the data in, that give you the CVR factor.
Yeah, but could it still be valuable to calculate if there were more than 20% constant power load on a feeder that it would never be beneficial to do CVR?
It would be actually interesting to look at it, yeah. Also depending on the zip model, right? Also low modeling is like another thing, how you model the load, yeah. Okay, yes, Trevor.
Is there any, like, does it make your system more vulnerable if you're lowering all these voltages?
Yes, so that's why you don't want to lower too low. So when remember I talked about the feedback earlier on the, where it's one. So usually they have a 2%, I mean, there's still 2% bound between the last houses should not hit the 114. Maybe they stay 116 just to give you a little comfortable room you can to move. Yes, Simi?
It would seem like CVR would benefit greatly from like reactive voltage support at the feeder, like way down to this.
Yeah, actually that's our continuum research. So the reactive power support scheme is actually we try to maximize the benefit of CVR by flattening the voltage profile. See, right now the constraint for me to lower the tap is actually the voltage for the last house, because you assume the conventionally the voltage should have monotonically decreased, right? So if you can somehow use the reactive power support to flatten out the entire feeder voltage profile, then you can do the maximum drop. Yes, and then you can see the more benefit of CVR. True, but you don't pay for the resistor loss, right? The industrial customer pay for it, but the residential we don't pay yet. Any more questions? Okay. Thank you. Oh, I'm early. Thanks.